All right, I'm going to continue with the simple harmonic motion from page 13, and then we're going to talk about the energy stored in the spring, or the energy of the whole system, including the object. Now here, this is elastic potential energy, that's energy in the spring. When you're all the way at the end, either at A or negative A or A, all your energy is in the form of elastic potential energy. When you are in the middle, there is no more stretch or compression, so all your energy is kinetic. But anywhere in between, you have both types of energy because you're moving and at the same time, you either stretch or compressed. So let's look at the different parts of this trip here. So if you are at negative A, assuming you started from A, after half a period, you're going to find yourself at negative A. So if you're at negative A, all your energy is in the form of potential energy. If you are at 0, all your energy is in the form of kinetic. If you go back to A, it's in the form of potential energy. And you can read the rest of this page, and you're going to see the different types of energy at different locations. Right. Here it says, in order to find the maximum speed, meaning in the middle, then all you have to do is work between these two equations here, these two expressions, and you're going to see that you can isolate V max, and if you get rid of the halves, you divide by m, and you take a radical, you should get V max is A times radical of K over m. Okay. So that's something that should be easy to do. All right. So I'm going to do some energy bar charts. And what I'm going to do actually here, I'm going to do it at different places. So I'm going to do it at position either A or negative A. Okay, at either one of those. So at position A, all my energy is potential. So this is U, and this is no kinetic here. Kinetic energy. Okay. Now let's see what happens at 0. In the middle, at the equilibrium position. It should look like this. There is no elastic potential energy because you are not compressed or stretched, and all that energy you had up here is in the form of kinetic energy now. And let's look at some other special cases. Let's say at A over 2 on either side, so plus or minus A over 2. So at A over 2, so I'm going to do 1, 2, 3, 4, 1, 2, 3, 4. Okay. At A over 2, because of the square on top of the x square, you only have a quarter of this energy here. So you should only have 1 bar for elastic potential energy. And the other 3 bars should be in the form of kinetic. Okay, so this is your kinetic energy. Okay, now the other thing we can try is we can try to figure out a place. I mean, this is not drawn to scale, but you got the idea. Okay, 3 bars. In other words, this 3 added to that one should equal to that height over there. Now let's try a location where okay. Let's try a location where U is equal to kinetic energy in terms of A. So at this location, I have 1/2 K x squared. I'm going to find the x here, right? Plus, I can do 1/2 m v squared equals 1/2 K a squared. And I'm setting it up so that my potential energy and my kinetic energy are the same. So I'm basically saying this, that this 1/2 mv squared is just 1/2 k x squared. So we can do something like that. So we have 2k x squared is k a squared, which means x is equal to plus or minus a over radical 2. So at this exact location on either side of the equilibrium, your elastic potential energy and your kinetic energy have to be the same. So if we go back to the bar chart, we should have 2 segments for each. So this is your potential energy and this is your kinetic energy. You can do this for, you can say, well, I want to find a place where my elastic potential energy is half of my kinetic energy. So let's see what we can do. So let's see. So we're going to do 1/2 k x squared, and you want your this here to be half of the kinetic energy. So basically you want your kinetic energy to be twice as much. So you want it to be twice that. Equals 1/2 k a squared. I hope that makes sense. Okay. So the U has to be half of the kinetic energy, which means the kinetic energy has to be twice as much as that. So if we can do this, we can maybe get rid of these k's. So let's see what we have here. So we have 3x squared is a squared. So x is going to be equal to plus or minus a over radical 3. And you can do this for all possible scenarios. All right. I'm going to try to make this smaller so we can fit everything in there. Okay. So the function here is x equals a sine omega t. Now keep in mind that this position time graph can be a sine or a cosine. It all depends when the time starts. So if you're trying to do the velocity here, it looks like the velocity starts positive because this slope is positive. So, and its maximum here, that's the steepest part, and it gets to 0, right? And then it gets to maximum steepness but negative, and then it gets back to 0, and then here it gets to maximum steepness and positive. Okay, so my curve should look something like this. Should look like a cosine function. If I do the acceleration, it's also going to be a sine function. It's going to be the same function as x, except that it's going to be flipped. And I think we've learned that before. So it's going to be upside down, x position. Now, these maximum values for v and for acceleration are not the same as the maximum values for x. And we talked about that, and I showed you how you can find those. All right. For elastic potential energy, this has to do with x squared, so it's going to follow. Here you have no elastic potential energy. When the speed is 0, you have maximum. When the speed is at the equilibrium, the speed is maximum, right? So you have no elastic potential energy in here. So now elastic potential energy is 1/2 k x squared, so it has to remain positive. In here you have no speed, so which means you have maximum elastic potential energy, and here you have no stretch, so which means you have no elastic potential energy, and your curve should look like that. Okay. All right. Here it should more like that. Okay. Now the kinetic energy is just going to be the opposite of that because the total energy has to remain constant at this value. So this one is going to look like that. Okay? So it's just going to be the flip. Okay. Now let's go back to our normal size. Okay. For number 21, an ideal spring is attached to one end of a wall and the other end to a mass M. The mass is set into oscillation along a frictional force by okay. So we're trying to find the K here. So I can say that 1/2 K x squared, which is really a square, is 1/2 M V maximum square. So I can get rid of that. If I want to find K, all I have to do is divide this by a square. So the answer should be D. All right, let's look at 22. A mass is attached to a spring with a spring constant K. If the mass is set into simple harmonic motion by displacement D, so instead of saying X, they called it D, from equilibrium, what would be the speed of the mass when it returns to equilibrium position? So here we just have to do 1/2 K D squared, that's your amplitude, equals 1/2 M V maximum square. So V is equal to D, I'm sorry, I crossed out the wrong thing, D radical K over M. So the answer should be D. Okay. For number 23, you're going to pull on something, right? Yeah, it's pulled at distance D. When released from rest, the block moves towards equilibrium. What coefficient of kinetic friction between the surface and the block would allow the block to return to equilibrium and stop? So we're going to do conservation of energy. Initially, I had all elastic potential energy the moment I released it, right? Okay. Plus, there is some work done by friction, and at the end, I ended up with nothing. It's not stretched because it's at the equilibrium, and it's not moving. So if I want to find, now the work done by friction, if you remember, is mu mg times the distance that it's going to travel. Well, it's going to travel at distance x, cosine of 180. Okay, so here I think we can just clean this up a little bit, get rid of one of the x's, and say 1/2 kx equals mu mg, and mu is equal to kx over 2 mg. So the answer is C. All right, let's look at 24. An object is attached to a spring and oscillates with amplitude A, period T. The nature of the velocity V and acceleration of the graph at time is best represented by which of the following? So at a quarter of the period, you are here. So this is T over 4. Okay. At that moment there, your velocity is 0 because the slope there is 0. And the acceleration has to be negative because we learned that the graphs of displacement time and acceleration time are flipped. Right, so we have to be here at D. Okay. All right, let's look at this RT3. All right, so they're giving us this first experiment A, and they're making some changes, and we're going to see what could have changed. Okay. Compared to experiment A, in experiment B, the cart has, well, let's see. I don't think the mass changed. See, the period remained the same, right? So here is one period, and here is one period. So the period remains the same. So since it's the same spring, okay, so t equals 2 pi square root of m over k. If the t stays the same and k stay the same, m has no choice but to remain the same. Okay. Compared to experiment A, experiment C, in experiment C, the cart has, well, let's see. So let's take a look at experiment C. In here, the period stops there, but the period for the other one is kind of like there-ish. No, it's here. Period of the other one is here. Okay, so it looks like the period here is just half as much as it was up here. So in order for the period to be half as much and the spring constant is the same, if you want to get half of that out here, you have to make the mass 1/4 as much. Because when you take the square root, you have to come out with a half. So the mass has to be 1/4 as much. Okay, there's an experiment D. The mass used in experiment A was doubled, and the spring was replaced with the spring with spring constant 2k. The period in experiment D would be, it should be the same, because if you double the mass and you double the k, you pretty much did not do anything. Okay. Now let's look at RT4. Okay, so the first question, what is the period of the motion of this cart? Well, the period is just 8 seconds. I mean, you just have to read from the graph. You just have to see one cycle. As soon as you start to repeat, you stop and you read that number. So it's 8 seconds. What is the frequency? Well, the frequency is just the reciprocal of period. So your frequency will just be 1 over period, 1 over 8. Okay. In which direction was the cart displaced from equilibrium before it was released? Well, it had to be pushed in to the left, because when it first started, it had a positive velocity, which means when it first started, it started moving to the right. So it had to be pushed to the left, because if you pulled it to the right, when you release it, it will have a negative velocity, and this whole thing will be flipped. A mass is oscillating up and down at the end of a spring. 3 students are discussing the acceleration of the mass. Okay, Eileen says, I think the acceleration will be largest when it is at the end of its oscillations turning around. That's where the spring is stretched the most. That's true, because that's when you have the maximum force, okay? And force is directly proportional to acceleration. So when you have maximum force, you must have maximum acceleration. So she's right. Okay, let's look at the other people. No, I don't see how that can be. Its velocity is 0 at that point, so its acceleration has to be 0. That's not true. If the velocity is 0, the acceleration is not necessarily 0, and I think we used the example of throwing something up in the air. At the very top, the speed is 0, but gravity does not take a break. Gravity is still acting on it. Okay, because if the acceleration was 0 at the top, it will just stop there. Okay. I disagree. The acceleration is largest when the mass is halfway between the middle and the end, because it's where the speed is changing the most. That's not true, because in the middle, the acceleration is 0 because there is no stretch. So Eileen is correct. Okay. A mass spring system consists of a spring with a spring constant of stiffness K and an end-stretch length L, connected to a cart of mass M resting on a horizontal frictionless surface. If the cart is pulled to one side a small distance and released, it will oscillate back and forth with amplitude A and frequency F. Okay, this is all stuff we know. Okay. Okay, identify from choice. Okay. How each change described below will affect the frequency of the oscillating mass spring system. Compared to the case above, this change will. Okay. Okay, so we're looking at, the mass is increased. So now we have to write the formula. T is 2 pi square root of m over k, and frequency is the flip of that, or the reciprocal. Okay, so if I increase the mass, so if I increase the mass, the frequency has to drop because there is an inverse relationship between mass and frequency. Okay, the spring constant of stiffness is increased. So if I increase K, there is a direct relationship between F and K. F will increase. The mass is pulled a little further and then released. So we're changing the amplitude, and we explained in class that the amplitude does not affect the period, and consequently it doesn't affect the frequency. Okay, the spring constant is double and the mass is reduced to half. Well, if you multiply the K by 2 and you cut the mass in half, so you basically introduced a factor of 4 inside the radical, which means a factor of 2 outside the radical. So the frequency will have to double. The amplitude is increased and the mass is increased. Well, if you increase the amplitude, that has no effect. But if you increase the mass, it's just like previously, the frequency will have to decrease. Okay. Now we're at RT7. A mass hanger in a vertical spring is pulled down at distance d and released. The mass undergoes simple harmonic motion. The 3 students make the following contention about the situation. Okay, Alexandra. The maximum kinetic energy of this mass spring system is fixed by the properties of the system and does not depend on how far down the mass is pulled. Well, that's not true, because if you pull, if your amplitude is bigger, if you pull more, which means you put in more work into the system, there will be more elastic potential energy stored, which will eventually, when you are halfway at the equilibrium position, will all become kinetic energy. So it depends on how far down we pull. It depends on the amplitude. All right, the next person. No, that can be right, since increasing the amplitude or how far down it is pulled increases the potential energy of the system. I don't think the amplitude has any effect on the on the frequency. Well, we have no yeah, that's true. The amplitude has no effect on the frequency. I agree in part with both of you. I think the amplitude does affect the maximum kinetic energy, but I think it affects the frequency of oscillations. No, the amplitude does not affect the frequency, but it does affect the kinetic energy. Let me see what Bruno said. No, that can be right, since increasing the amplitude or how far down is pulled increases the potential energy of the system. Oh yeah, Bruno was right, because I read this as the amplitude has an effect. Yeah, so the amplitude has no effect. So Bruno is the one that's correct. Okay? Yeah, because the more amplitude, the more energy is stored in the spring, and the more kinetic you're going to end up with. Yeah. Yep. Okay. Let's do this energy bar chart. Okay. At point A, we have to turn around. So there's no kinetic energy, and our potential energy is 4 bars here. Okay. At point B, which is halfway the maximum displacement, because of that x squared, we should have, at the halfway mark, we should have a quarter of the potential energy. So a quarter, so 1 bar is elastic potential energy, and 3 bars have to be the kinetic energy. And here at point C, there is no stretch, which means you have nothing here. at point D and point B are symmetrical, right? So it should look the same. And point E should be exactly the same as point A. Okay. So just keep in mind that when you're halfway, the maximum displacement, a quarter of your potential energy is, a quarter of your total energy is potential, and the other 3/4 are kinetic. All right, let's look at RT9. A cart attached to a spring is displaced from equilibrium and then released. Okay, so they're giving us a displacement versus time graph, no friction. Okay. Okay. At which point or points are the spring potential energy and the cart kinetic both at their maximum value? They can never be at a maximum value at the same time, right? Because when one is maximum, the other one is minimum. Okay. At which point or points is the kinetic energy equal to 0? Well, it's equal to 0 when it stops and turns around. So it should be points A and E. At which point or points is the total energy at its maximum value all the time? Because we're talking about total energy, and total energy stays constant no matter where. Okay. At which point or points is the spring potential energy negative? It's never negative because of that x squared. So both kinetic energy and potential energy are both positive. Okay. Energy is a scalar quantity, so we can't talk about the negative part of energy. Okay. At which point or points is the kinetic energy positive? Well, it's going to be positive whenever it's not 0, right? So it's going to be positive at B, C, D, F, and H. And G, right? Because it's still moving at G. At which point or points is the kinetic energy at its maximum value and the spring potential energy that is at minimum value? So the potential energy is at minimum value when there is no stretch, okay, which means C and G. And if the potential energy is at minimum, the kinetic energy has to be at maximum. You can also look at it as the speed at C and G is maximum because that slope or that segment is the steepest, okay, in those areas. At what point or points? At what point or points is the kinetic energy minimum and potential energy maximum? Well, kinetic energy is minimum at A and E because it's not moving, and potential energy is maximum at those points because that's where you have maximum stretch or compression. And that's it.